1967, what his equations implied, buried in the mathematics, was an inevitability. The sun brightens by roughly 1% every 100 million years, and that brightening does not stop until the fuel runs out. 14 years before Beta, in 1925, a 25-year-old astronomer named Cecilia Payne-Gaposchkin had already found the crucial foundation. Her doctoral thesis at Radcliffe College demonstrated through spectroscopic analysis that the sun is composed overwhelmingly of hydrogen. Her supervising advisor, Henry Norris Russell of Princeton, pressured her to call the findings spurious. 4 years later, Russell independently confirmed the result and published it as his own discovery. Payne-Gaposchkin's credit was eventually restored, but the implication of her original finding remained. The sun's primary fuel is finite, the waste product is accumulating, and the engine is not what it was when Earth first formed. In 1972, Carl Sagan and George Mullen formalized what the geological record had already suggested 4 billion years ago. The sun was roughly 70% as luminous as today, which should have left Earth as a frozen ball. It was not. Ancient rocks show liquid water, oceans, rain. The atmosphere compensated then. It will not compensate forever. That negotiation between Earth's climate and a brightening star has been running for 4 billion years. It is running out of room. For most of human history, the practical dangers of the sun and its long-term evolutionary threat were treated as separate problems. One was urgent, one was urgent. On September 1, 1859, British amateur astronomer Richard Carrington was sketching sunspots when he witnessed something never before consciously recorded: a sudden brilliant brightening above two sunspot clusters. He noted the time, 11 a.m., and wrote it down. The following day, telegraph systems across the world failed and sparked without power. Aurora borealis appeared over Cuba. Papers in Boston caught fire from electrical discharge. The Carrington event remains the strongest geomagnetic storm in recorded history. Scientists studying ice cores have found evidence of a solar particle event around 774 CE that may have been 20 times larger. In March 1989, a storm 40,000 times weaker than Carrington collapsed the Hydro-Quebec power grid in 92 seconds. 6 million people lost power, 40,000 times weaker. The infrastructure that a Carrington-scale storm could now destroy, continental power grids, satellite constellations, hospital systems, financial networks dependent on precise timing, did not exist in 1859. Today, the warning time for an incoming coronal mass ejection is 15 to 60 minutes. For a civilization built on electricity, that is not a long time. In May 2024, a G5 geomagnetic storm, the highest category on the NOAA scale, struck Earth for the first time in 21 years. GPS agriculture systems failed across the American Midwest during planting season. Transformers in Europe required emergency protective shutdowns. The G5 storm of May 10, 2024 was the first of its kind in 2 decades. That is not the end of a story. It is the first sentence of one. Earth and Venus were built from the same solar nebula at the same time, from the same materials. Venus orbits 26% closer to the Sun. That 26% difference produced a runaway greenhouse effect on Venus long ago. Today, Venus has a surface temperature of 465 degrees Celsius, hot enough to melt lead, under an atmosphere of carbon dioxide so dense that the Soviet Venera 7 lander was crushed and destroyed within 23 minutes of landing. Same origin, same solar system, same star. One is this, one is that. The mechanism that made Venus what it is has a name: the runaway greenhouse limit. Climate models developed by NASA's James Casting in the early 1990s placed that limit for Earth at approximately 1.1 times the current solar constant, a 10% increase in luminosity. At current brightening rates of 1% per 100 million years, that threshold arrives in approximately 1 billion years. When it does, the cold trap of the tropopause, the atmospheric boundary that currently keeps water vapor low, cycling it back to the surface as rain, weakens. Water vapor penetrates the stratosphere. Ultraviolet radiation splits the water molecules. Hydrogen, the lightest element, escapes Earth's gravity permanently and bleeds into space. The process, once started, does not stop. The models suggest complete ocean loss within 1 billion years of threshold crossing. Not dramatic, not visible, not marked by any sound or sensation. On the day that threshold is crossed, nothing special happens at the surface. The sky is still blue. Whatever life exists still moves to this day. The change is in the energy budget, in fractions of watts per square meter arriving and being retained. But the process, once past that threshold, does not stop. It cascades. More heat evaporates more ocean. More vapor traps more heat. Less ice reflects less radiation. Less reflection absorbs more energy. The system is not linear. It feeds itself. In approximately 5 billion years, the Sun swells into a red giant. Its radius expands to between 100 and 200 times its current size of 432,685 miles. At 150 times current radius, its outer atmosphere reaches within 28 million miles of Earth's current orbital position. Some models place the maximum expansion past 1 AU entirely. Mercury, gone. Venus, gone. Earth, at minimum, a bare rock exceeding 1,000 degrees Celsius, stripped of every ocean and every molecule of atmosphere long before the expansion completes. The oceans are gone before the red giant arrives. They are gone not because the Sun engulfs the planet. They are gone because the planet's atmosphere cannot hold water against an increasingly energetic star. Complex multicellular life, the kind this planet currently hosts, has perhaps 500 to 800 million years remaining before conditions deteriorate past survivability. That is less time than the dinosaurs have already been extinct. In 500 million years, at 25 years per generation, 20 million human generations will have lived and died between now and that tipping point. 20 million generations of descendants carrying forward whatever knowledge and capability this civilization manages to build. That sentence alone is worth sitting with. In 2001, astronomers Don Korikansky, Gregory Laughlin, and Fred Adams published a paper proposing orbital migration, using repeated gravitational assists from a redirected asteroid or Kuiper belt object to gradually expand Earth's orbit outward as the Sun brightens. The physics is sound. The engineering does not yet exist, but the timescale is long enough that current capability is not the immediate problem. The immediate problem is whether civilization survives intact long enough to develop it. All of that is contingent on surviving the short-term threats first. The radiation environment near solar maximum causes measurable biological damage. The same star that will eventually strip Earth's atmosphere is, right now, producing X-class flares at elevated frequency during solar cycle 25, a cycle that reached its maximum in late 2024 and early 2025. Every coronal mass ejection aimed at Earth is a reminder that the long timeline and the short timeline are not separate problems. They are the same problem. Mars offers one data point. It lost its global magnetic field early in its history. Solar wind then eroded most of its atmosphere over billions of years. Surface pressure today is less than 1% of Earth's. Ancient Mars had liquid water. The evidence sits in delta formations in Jezero crater, in minerals that form only in the presence of flowing water. The same solar wind that is currently a manageable inconvenience for Earth was sufficient, over time, to render Mars unlivable. That is not a distant projection. That already happened. The same star that rose over the Serengeti 3 million years ago while early hominids shaped the first stone tools is the same star rising over this planet right now. The same proton-proton chain. The same 600 million tons of hydrogen per second. The same engine. Everything that has changed on the side of the planet, not the star. The star does not notice. What changed in the last 100 years, is that we looked anyway. Cecilia Payne-Gaposchkin looked at the spectral lines and saw hydrogen and published it, despite being told not to. Hans Bethe looked at the fusion equations and wrote down how long the Sun had left, and filed that number honestly. Richard Carrington, on a September morning in 1859, watched a flare brighten above a sunspot cluster, noted the time, and wrote it down. Not because someone asked him to, because it was true, and truth required recording. What changed is that they went anyway. In Jezero crater on Mars, a rover named Perseverance is drilling into sediment that may contain fossilized evidence of ancient microbial life. Organisms that survived until the atmosphere was stripped, until the water was gone, until conditions crossed a threshold they could not survive. They did not know what was coming. They simply persisted as long as conditions allowed, and left their record in the rock for another species to find 4 billion years later. The difference between that life and this one is awareness. Awareness of the equations, awareness of the threshold, awareness that the dial is turning, has always been turning, and will not stop. The question is not whether the Sun one day takes this planet. It will. The question is whether the species that first decoded the mechanism treats that knowledge as a grief or as a map. Thanks for watching, and I'll see you in the next one.